So I'm going to, in case Aiden and Rosie would like to watch, or any of us. All right. So this chapter is all about, we're continuing to apply H. Now, this, of course, is enthalpy, and we know based upon the sign how we interpret that. And we talked about different ways we find it. All right. But now we've gotten this S term. And then today, we are really going to dig in to Gibbs free energy. What I would like to do is to warm up with some questions that employ S, then learn more about, okay, so what is this Gibbs free energy? And why do we give it that title of being kind of the end of the line decision maker about thermodynamic favorability? So can we do some warm-up questions where we're asked to judge the sign, but then find the value of S, learn some more about G, how do we find G, actually find values for G, and really see the role of enthalpy and entropy on thermodynamic favorability, but also G can reveal K and K can reveal G. So we'll see that. Dun, dun, dun. And then I have for us a selection of multiple choice and kind of a really comprehensive kind of free response that will tackle all of this for us. All right, so to warm up, your packet is green or maybe white. It is the sample of multiple choice, not our unit packet, if you will. So if you do have the different colored, it's green, but you may have white. So can we turn to the back of the second page, the back of the second page. Okie dokie. So can we address question 16? This will take a minute because we do have to calculate, as well as on the next page, can we tackle number 8? So on the back of 2, number 16, page 3, number 8. Okay, dig in. So much of thermodynamics, we see these kind of summation equations. So we learned different ways. I'm just going to get there so quick. We can find H through calorimetry. We can also find H of a reaction by summing up the enthalpies of formation of product minus the enthalpies of formation of reactant. Well, we can find the change in entropy by applying, and look, in this table right above, we have enthalpies of formation, Gibbs free energies of formation, and absolute entropies. So that is a way, if we have absolute entropies of everything, that we can find the change in entropy of the process. So, yeah, is it coming back or no? Go ahead. Oh, yeah, a little bit. Okay, so all we have to do is just go up in the table and find. Now, these are applied values. They are just derived from the third law of thermodynamics, which says if we have diamond at 0 Kelvin, the entropy is 0. Okay, what if we're at 25 Celsius or 298 Kelvin? Yeah, well, then it's going to be this value in joule per Kelvin mole. All right, but I have C2H2 gas. So I just look and whoop, 200.8. I find the values, God bless you. And I will give you the equation, which says, okay, sum up products minus reactant, taking into account the coefficients of the balance equation. So 4 moles of CO2 times the 213 point, and so on and so on and so on. And we should get E. Now, Stephen, that is a way to find the actual numerical value. Could you have anticipated the sign as expected to be negative for this process, and why? Okay, you're so right. So we have gaseous reactant, and sorry that oxygen has been ignored to be gas. So we start with 7 moles of gas as reactant, and then we go to 4 moles of gas and then a liquid. So we are decreasing dispersion of reactant compared to product. So we would definitely anticipate that it's negative. Okay, questions? Okay, does that seem like that came from some alien species that we've never talked about before? 8. So I think we already looked at this, but this is a nice summary of, okay, how can we judge if entropy changes? And just like there are certain relationships we just know and don't have to explain. Temperature is directly related to kinetic energy. Remember, that was conveyed to us in the gas unit. You can take that to the bank. We just know that. We don't say, according to the kinetic molecular theory, we just know that. Well, what else do we know? Well, entropy being dispersion, for example, increases as we increase temperature. As we increase temperature, we increase entropy, because those go hand in hand. Increasing temperature, we know we can just say increases dispersion, and so on. Yeah. Okay. So number 8, are we okay? Which of the one would have the greatest increase? Well, actually, this is the only one that is increasing dispersion, because we have solid making solid, and then 3 moles of gas where we didn't have any. This, oh my gosh, we are decreasing dispersion. We're going from the most dispersed state of matter to middle, quote unquote, not yet solid, but less. Solid gas to solid, so we're decreasing. This would be negative, negative. And then 4 moles of gas to 2, negative. We're decreasing dispersion. Yeah. Okay, questions? Okay, so can we confidently judge sign and then apply the absolute entropies of product minus summation of absolute entropy of reactant, but of course taking into account the balanced coefficients. Okie dokie. So continuing onward. And if I could go to, okay. And, you know, as AP teachers, collegiate professors, I did not change as I wanted it to. I'm so sorry. There we go. All right. There's not like a magic word, but we need to get proficient in the correct vocabulary. So dispersion is a wonderful, wonderful go-to. We can also use microspace or positional probability. Yeah, so we've gone over this. All right. So we're good, we're good, we're good. All right. Gibbs free energy. So what is Gibbs free energy? And we just went over, okay, how do we judge the sign? And remember, Stephen got a slam dunk with his correct answer to what if Gibbs free energy is 0. Okay, so why is this the granddaddy term? All right, so Gibbs free energy takes into account our entropy and enthalpy. So just to make sure. And remind us, Elena, what does it mean if we have that little floating 0? Great. So what temperature? Isn't it so unfortunate? It is so unfortunate that we have standard temperature and pressure and then standard state. That is mean. So we have standard temperature and then standard pressure that apply to STP, but then we have standard state. That is so mean that we use that same precursive adjective. Is that what we would say? Descriptor. Same word. Oh, okay. STP is 0 Celsius as far as standard temperature, and which would be 273.15 Kelvin. Standard pressure, 1 atm, which is also equivalent to 760 millimeters of mercury. Okay. We employ STP conditions mainly with gases because at STP, 1 mole of any gas will occupy 22.414 liters, called molar volume. All right, that's the whole reason for that, kit and caboodle. And there's some other, but not for our intensive purposes. So then what the heck is that floating 0? That means standard state. Chemists, you need to do a better job, because at standard state, pressure is the same thing as standard pressure, 1 atm or 760 millimeters of mercury, but temperature is room temperature, 25 Celsius or 298.15 Kelvin. Isn't that just not nice? Just not nice. So, oh, and then if we have a solution, it'll be 1 molar in solute, which will become important next chapter for us. So that's what that floating 0. So Elena, isn't that just so mean? So really the only difference is temperature. we're at, as you said, room conditions. Yes, yes, yes. Okay. Thermodynamically, we have already said this. So we know enthalpy, we are thermodynamically favored if it is negative, and if our change in entropy is positive, and temperature is going to be in Kelvin. This will always be a positive term if this is positive, because your temperature is always going to be positive. But we don't always have the entropy change as positive. Okay, so if you want in your notes to, but we'll talk through this. We will talk through this. Okay, so our enthalpy can be exothermic or endothermic, and our change in entropy can be positive or negative. Now, Ryan, can you remind us, sir, as far as Gibbs free energy, what sign is thermodynamically favored? Yeah. Okay, so I'm going to recreate this and then take it off the screen. Okay. So, all right. And it's positive, 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 negative, negative, positive, negative, negative. All right. Okie dokie. So, under what conditions, that's what we're trying to say. When are we thermodynamically favored? Always? Never? Or the temperature matters. So we're going to have always thermodynamically favored, no matter the temp. Never thermodynamically favored, no matter the temp. Or will be thermodynamically favored at high temp or low temp. So we have all those different possibilities. So, thermodynamically favored or spontaneous? Okay, so which is the always? All right, go. You got it. So when we're exothermic and increasing entropy. So this is at all temperatures or always. There are very few of those in chemistry, aren't there? Black and white. That is black and white. Ryan, is there a never? Yeah, whenever we're endothermic and we're decreasing entropy, no matter what, can't get this to be negative. So not thermodynamically favored at any temp. So the only way that we can get that process to occur is if we invest energy. This, no matter the temperature, once we invest activation energy, if needed, it's going to go for us. We don't have to invest anything. And remember, it doesn't mean fast. It just means thermodynamically favored. Okay. So then, all right, if we are endothermic, we want this to be negative. Okay. If this is positive, what we need is for the value of this term, because if this is positive, temperature is always going to be positive. So we're not going to undo the subtraction. So what we need is for this to be greater than that. So we just say, well, what's going to deliver that? A high temperature. And that is so generic. What do we mean by high temperature? Well, it depends on these values. Whatever will just start to put us over. So this will be a negative value. As soon as we get a temperature that makes this more negative than that is positive. So no worries. And so the positive, it'll be thermodynamically favored at high temp. And again, how generic. High temp. And then if we have the last scenario of exothermic, well, that's in our favor. Oh, but what if we're decreasing entropy? And then, bless you, and then this is always going to be positive. So we're going to end up making a positive term. And if this is bigger than this, then this will overwhelm that and make that positive. So we want to make this little. And so at low temperatures, okay? Okay, so we want this to be negative, and then period, end of story, the process is thermodynamically favored. So that is something that we can recall, just like kinetic energy is directly related to temperature. Well, this means thermodynamically favored under the conditions written. All right, so let's look at some sample questions. All right. So, what do you guys think? Why? Very good. And so it's about making the T delta S term larger than this. And so at a higher temperature, then this will be negative because you're subtracting it, and we'll make it a negative G. Excellent, excellent, excellent. Yes, sir. No. Why is that? What would? Are you? No. Oh, do you see? And Ryan, you are so bright. So we can't fall for that. What error? Yes. So I get it that you were just looking at, oh, well, what do I need to multiply this by? Ah. So that is 0.090 kilojoules. So a little greater than 7 Kelvin is in, yeah, that's why. Yeah. So if we just think standard state is 298, so we're talking about greater than 298 Kelvin at least. So thousands of Kelvin. High. Yeah. And it doesn't necessarily always mean 1,000 of Kelvin degree, but in this case it does. Yeah. Ryan, thank you for putting yourself out there and for being vulnerable enough to take the correction. I'm not sure if Kyle could. I know it. No, he would be like, but I can dance. And he'd like throw a move out and try to distract us with that. I'm sorry, Rachel, what did you say?
I said we still gotta see him, Kyle. We haven't seen him. Oh yeah.
We all get 5s.
Yeah.
Everyone else.
Yeah.
All right. Now, what we have to be on guard for are clues or giveaways within the wording. And we know we're hesitant to read all the wording. For example, okay, we see the reaction. Oh, we're given the enthalpy. That's good. Oh, but look here. The reaction is thermodynamically favorable. So we know negative delta G. Done. So they're asking us for the signs. Thermodynamically favored. Delta G is negative. Delta G is negative. A and C are out. Just based upon that wording. Yeah, A and C are out. So how do we judge if delta S is positive or negative? We look at our reaction. Okay, so what are we doing? Increasing dispersion, decreasing dispersion. We look at our phases, go. Perfect, I wanted to make sure I heard it correctly. Increasing, we're going for aqueous, which isn't too bad, to liquid. Now aqueous would definitely be more dispersion because we understand that's dissolved in water. So we'd have two different substances, so we can have more microstates versus a pure liquid, but it's the production of the gas that definitely seals the deal. And so then delta G is negative, delta S is positive. Okay, can we go back to the green packet or white, if that's what you're taking a look at? All right, so can we take a look at what I finally have a letter, page F. I think it is what, the back of the third page, back of the third page. All right. Can you think about how you would answer? I encourage you to write down if you want to scribble down some answers. Now we understand that now in our modern times, a free response wouldn't say, why is that? It would say, justify why. Or the delta H value is positive, explain, period. So the two ones that I have arrows on, can we think about our responses? And then we'll chat. All right. So we wouldn't have to relate that, okay, if delta H is positive, that means it's endothermic. But we know that means heat is required. Why here? Go. Can I ask you this? D. What is your answer to D? Yeah. There's no change in temperature during a phase change. Okay. So you said, right, that you're boiling, you need to increase temperature. Why? During a phase change, what is being accomplished? On the particle level.
So you got like.
Maybe if it's to overcome. Okay, AP students, we're going to answer this question and we're going to knock the socks off the AP reader that's reading yours, because we're not just going to say particle attraction. We're going to be specific about what particle attraction. CH3OH. So this would be carbon, 3 hydrogens, oxygen. So They're helping you with the structure. Go. Is that a chemical bond, Steven? Excellent. Sorry. Can I have some of the, no, just kidding. Back. No, just kidding. You disearned some of your fruit juice. Just kidding, just kidding. Sophia, the Walmart Smiley gummies, tangy. Smell.
Hey, thank you, Kyle. Thank you, Kyle.
Okay to share with, but not sit next to.
Kyle and I are buds. We yelled for Kyle during the send off.
I'm sorry.
We yelled for Kyle during send off.
Heck yeah, he heard us. All right. All of you can earn. All of you can earn. Okay, say that again. To overcome what? So, what has to be true about this to have hydrogen bonding? Go. Yes. But even before that. So we know 3 intermolecular forces. So what we could say is to overcome intermolecular forces. But even better, what is the strongest one holding it? There's 3 intermolecular forces, all molecules, one dispersion. And that's based upon the movement of electrons. And the bigger the molecule, the larger the number of electrons, so the more polarizable. Next, dipole dipole. And what has to be true for dipole dipole? Yeah, it has to be polar. And then if it's polar, which heck, it's going to be polar if we have hydrogen bonded to these very electronegative elements, that makes this a very, very high electron density area. And so when attraction forms, oh, it's going to be pretty strong. So we have to invest energy to overcome that and then transition to the gaseous phase to overcome the hydrogen bonding. We just have to be careful because I'm going to just, yeah. They're primarily, May 2nd, going to ask us about phase changes within molecular substances because they want to make sure that we know that you're not breaking chemical bonds. If we're breaking chemical bonds, then we're performing a chemical reaction. This is just a phase change. So usually they want to make sure if you have had 2 years or an intense study of chemistry that we understand that phase changes were not breaking and forming chemical bonds. In ionic, we are though. Right now. But that you're gonna have to use hundreds and hundreds of degrees Celsius. So commonly that's not what we're doing. So that's why we just have to be careful with that term bond. Okay. All right. So that is excellent for A, I, and II. That's all we needed. All right. Let's look at this this problem in number 5. Can we answer A, B, and C? A, B, and C. Okay, are we good that we would absolutely confidently say the sign on the change in entropy would be negative? Because you're going from one of your reactants being in the gaseous state to none. And not only that, you're just resulting in solid. So we are decreasing dispersion because you're going from gas to solid, therefore decreasing in entropy. You are told it's thermodynamically favored. So we know that means negative delta G, period, and move on. So then, well, what happens to the value of delta G as temperature is increased? So we are told that delta H is negative. Okay, that's in our favor. But delta S is negative. And so this is always going to be positive. So this will become a positive term then. So as we increase temperature, the value of delta G will increase. Right? It's going to move towards 0. And then and that means right on the number line. So if we say that, or move towards 0. Okay. Brain break. And then can we do 2 other examples and then we'll dig into our problem solving. Okay, there we go. All right. So we understand how we interpret the sign for delta G, but how do we find the actual value? There's 3 ways. So 1, a summation, and we'll be using Gibbs free energy of formation. And remember, the very back of our packet, we have that table of thermodynamic quantities. Well, the middle table is the Gibbs free energy of formation. And so we would just have to employ the correct value, employing, of course, the balanced coefficients. Okay, this is the most used thermodynamic equation. I know I said that yesterday. So that delta H minus T delta S, we've talked about that. We'll practice employing it in just a moment. And then if we are at equilibrium, it's been experimentally determined, and we'll apply that as well, that we can get delta G if we know the value of K, or if we know delta G, we can get, wait, did I say that right? If we know K, we can get delta G. If we know delta G, we can get K. All right, so, yes. Yes, you do. And so that's definitely assumed to be there. We would. And so if we're not going to solve this, we'll just look at this. So here is a hydrate. We don't often see those, but we encounter them throughout our daily life. And that's where an ionic compound has incorporated water in its structure. And with heating, you dry the crystal first. So that's why we write that water as a dot. So we haven't seen that for a while. So that is considered to be one reactant. So we're given the enthalpies of formation of product and the reactant. So we would take 1 times this negative 1320 plus 2 times water minus 1 times that. Easy peasy. All right, the delta G will be in kilojoules per mole. All right, so let's, to make sure that we don't drop the ball with units, let's go ahead. You can just watch me do it. Totally fine, totally fine. So, and I'll just write down my givens and then show us on the screen. So we're given our reaction. It should make sense to us, since we have 3 moles of reactant to 2 moles of product, that our delta S is definitely negative. We would never be expected to know that's exothermic. No. So we're given it. Okay, so we're asked to find delta G. All right, so it is, let me just get down these values and then 189.6. Okay. So, all right. You just plug and chug that. That's kilojoule per mole reaction. Which remember, it's okay if it's there or not there. Well, our temperature, we're at 298 Kelvin. So 25 Celsius plus 273.15. So 298.15 Kelvin. Now, we just have to be careful. This is joule per Kelvin mole. And so we're going to have to get ourselves 2 kilojoules because delta G naught is often in kilojoules. And so 1,000 joules, 1 kilojoule. So just being careful with our signs, but also our units. All right, so negative 196.6. And this negative and negative will make this positive. And we will have 4. And the Kelvins cancel, so kilojoule per mole. All right. Negative 140.1. And we could put per mole of reaction. Kyle, what do we conclude based upon that sign? Perfect. Perfect. All right. Now, we also saw that is the equation that relates Gibbs and K. All right. So if delta G naught is negative, that means thermodynamically favored. What does that mean? The reaction will be moving toward product. So we would anticipate we have more product versus reactant. So what will our K value be? Greater than, less than, equal to 1? You got it. Now, natural log. When my morning students were practicing, they were making errors because they were applying a logarithm, just being used to pH, I guess, calculations. A natural log. Now, if you're taking the natural log of K, if K is greater than 1, it's positive. So this will be positive. We know our temperature in Kelvin is going to be positive. R is a constant. So it's only when K is greater than 1 will it deliver a negative delta G naught. Or if delta G naught is negative, the only way that can happen is K is greater than 1. And then if it is not thermodynamically favored, we know that means, oh, it's not really producing product. We're going to be favoring reactant, which means K is less than 1. When you take the natural log of K and the value is less than 1, it's a negative number. Yeah. So natural log of, give me a number, Ryan, less than 1. Can we have a K that's negative?
Oh,
That's okay. We're going to get a negative value, which then, if this is negative, it's going to be positive, positive, it's going to make that positive. So we can see the relationships. Okay, now, R, we've been seeing that for a little bit. R is our gas law constant, but the only time we ever use it with gases, PV equals nRT, is when we use the 0.08206 liter atmosphere per Kelvin mole. We may be working with gases, but here, this is going to be Kelvin. This, doing the natural log, we're finding an exponent. No, this won't have a unit. So how on earth do we get kilojoule per mole Well, here's where we use, and I will give us always constant values, 8.314 joule per Kelvin mole. All right, so we just have to be careful because our delta G is probably going to be in kilojoules. It will be. And we're using R. So it's either, if we're trying to find K, if this is in kilojoules, we either convert this to joules or this to kilojoules. All right. Can we do one more question together? Sorry, 2, multiple choice. And then it's turned over to you. All right. Back to our green packet. I've indicated this is page G. It is the 3rd from the back, or page 4, I think. Yeah. So can we answer these 2 multiple choice, please? $15 more seconds and then. To make sure that we really are forcing ourselves to read, we don't want to miss. Whenever it says occurs without the addition of energy, we know delta G naught is negative. So we can get rid of D and get rid of A. All right, we can judge the sign on delta S by looking at our phases. We are decreasing dispersion, so delta S is negative. Oh, shoot, that didn't help. Well, I mean, they're both there. So we have to figure out what's going on here. Well, we know this is negative from that. We know this is negative from that. So if this is negative, we know this is going to be a positive. So, shucks, this is going to become or be a positive. If this is negative, it must be because of the delta H being negative. And so, B. And then for 12, you are freezing. You are freezing water. Okay, no go. Are we increasing entropy? We're decreasing it, going to the least dispersed phase. The value for delta G is 0. We don't know that. We could be just stagnant. We could have liquid going to solid and solid going to liquid. We're not giving or removing energy, but we don't know that. The value for this is negative. Is that exothermic? Liquid to solid? Oh gosh, never mind. I was going to bring up something, but it was somewhat politically related, and I don't want you to. Never mind. Do you know what I was going to say? I guess someone during the State of the Union address kept going like this. It was a little bit weird. Like, what does that mean? So what does that mean? I guess. Yeah. So I didn't know if like, is that code for something? I have no idea. But we're talking about molecules. Guys, now I do not have the luxury of having a refrigerator that like, ladies. What who said?
You said.
Oh, because?
I didn't know who that was.
Do you know who it is?
Yeah.
Oh, you, okay. And that's what, okay. So I didn't want to make a, anyway. Okay. Or have you ever like been in a cloud storm and they have those like little refrigerators? Have you ever like gone near the back of it and observed if it's cold or hot? Yes, yes, yes. Why? Because to freeze, you need to remove energy from your materials. Where does that energy go? To the surrounding air. And the back of your refrigerator, you guys ever, I'm sure you've seen a little refrigerator, the back of it? No, you will if you have one in college.
It's so funny.
A two-door, so I don't know, usually the back is open and you just see the coils. That's what's back hidden in your cabinets. Believe me, I don't have the luxury of that. So anyway, maybe because I don't know, but anyway, that is to release the heat and you don't want to keep it in there. That's why it doesn't have a back on it. Anyway, it is exothermic. We are expected as AP students to know very few processes are exo or endothermic. We are expected to know that combustion, for crying out loud, burning is exothermic. If it's a hydrocarbon plus oxygen making carbon dioxide and water, we're just expected to know that. The other thing are our phase changes. Okay, if we go from solid to liquid to gas, that is endothermic, where the reverse is exothermic. So is D correct? Heck yeah, but let's check. Is this thermodynamically favored under, and I love that Elaine, you said normal conditions. Does water freeze at 25 Celsius and 1 ATM without us doing some work? Heck no. So see all day long. The only other process that we're expected to know is endo or exo would be if we're breaking bonds. So if it's Cl2 to 2Cl, oh, false, ionization energy, endothermic, the energy required to remove electrons, and then electron affinity, but that's usually not asked about, so I may suck it. Okay, oh my gosh. You need to have pity on me because my heart is being broken by the looks on your faces. I know you could care less because I'm just the teacher, but I just want to just cry. I want to go home and get my puppy because he thinks I'm neat because I feed him. My kids are so impressed. The chickens get all excited when I pull into the driveway. That's because they know I'm the food person. That's it. They don't know I'm me, just I'm the food person. Same with my dogs. And I also take them for walks. I give them food, but that's all right. I don't know. Anyway, that's okay because it's not a pity Gerhard. It's just a, man, you guys are so great. I love you so much. All right. So here, all right. I think it would be best. Oh, for heaven's sakes. Not you, sir. Oh, for crying out loud. See, I'm just discombobulated. Too many white papers. That's why I need to color code everything. Like just too many. Oh, for heaven's sakes. Kyle, where did I put them, sir? No? No? Scared.
She did. Was she collecting on
Oh, for heaven's sakes. Okay, could you turn to what I think is the third page? And not that you ever maybe absorb this, I wonder if, that's good now, that's there. Okay, if you ever observe that your teachers provide you a whimsy kind of worksheet. Well, anytime, I can only speak for chemistry, of course. So anytime that it's these super problems, that pretty much is like the most extensive free response on the topic that you could get. And it usually is combining probably 2 free response because it's trying to hit on all the areas of the concept. I just want to really, really examine the new thermodynamic terms. So this whole first part of the question deals with enthalpy. We already know how to do all this, but they also did not provide us the density of the solution, which they really needed to. So we're just gonna start. So with the remainder of our class, this is where I would start, and you're fine not having answered that. Just begin as if this were part A. But we will then kind of get exposed to, okay, what do we need to do with this information? All right. Can I share one more thing before I turn it over to you? So what I would do is start here, answer. I have keys that you can compare your work to, ask me for clarification. After going through this, then I'd start to hit the multiple choice questions. There are a couple in here that aren't specifically thermodynamically related, so just the ones that I've circled. Okay. The only summation equation that does not involve product minus reactant is when we have bond energies. I do hesitate ever sharing something that I think is way too elementary or childish. But a teacher shared this with me, and man, it has stuck with me. So I hope that we just get the meaning. Bond energies are reactants first. Bond energies are reactant first. So in L, they're asking us to employ this relationship that we can get the enthalpy of the reaction by summing up, but this is the only summation where it's the bond energies of reactant minus the bond energies of the product. That's the only one. Every other one is product minus reactant. So that just is a good reminder of that. So bond energies are reactant first, because they could ask us that and they don't provide this equation. But they do all our other on the May 2nd task. Okay, so you have keys, you have me. Let's just get the most out of our last 14 minutes. Yes, you definitely may